I am so very happy to have been invited back to share this with you. As you heard in the introduction, the last time I was here, it was to give an overview of the Bell X-1 program and the first supersonic airplane. This is part two of that. This is who else was there. So I'm happy to be here with you this morning. Thank you for wearing your red blazers. Because you are the keepers of the flame. I say keepers of the flame, it's where are we today and how did we get here? And people don't know that through osmosis. Somebody has to tell them. So thank you for the work you do. So why do we say that the D-558s, the -1 Skyrocket and the -2 or the -1 Skystreak and the -2 Skyrocket. Why do we say that those are the X-planes that should have been? Well, it's 6 airframes. They had a famous designer, Ed Heinemann, who worked at a famous company, Douglas, in a famous place, El Segundo. And Douglas did the Sky Raider, the Sky Ray, the Skyhawk, the Skystreak, the Skyrocket, and many more. They flew in the same high desert as the Bell X-1. They took off and landed on the same lake bed. They used the same rocket engine as the X-1. And they worked shoulder to shoulder with the X-1 team for a decade, from 1947 through 1956. They set official world air speed records, something the X-1 never did. They had Mach milestones, they had altitude record flights. The X-1s in total flew 237 flights between 1946 and when that program ended in 1958. The D-558s flew 547 test missions, 547. So they were there holding up their end of the show. The movie The Right Stuff, however, tells you all about the X-1, tells you all about some guy named Chuck Yeager, but when it comes to the D-558s, they swerve around that like it's a flat skunk on the highway. It's just not part of the story. And the other thing, this is San Diego, so the other thing that I want to share here is this is the early days of flight research. These are the first purpose-built flight research airplanes. And the D-558 program marks when the United States Navy and the Marine Corps showed up to hold up their end and put points on the board for the team. The Navy was there too. So I'd like to make some quick acknowledgments here. Just to share, these are the people whose shoulders I stand on here today to be able to share this story with you. They're colleagues, and most important, I am very happy to call them friends. Dr. Richard Hallian, Dick Hallian, wrote the books Supersonic Flight and On the Frontier. He started working on the X-1 story and the D-558 story when the National Air and Space Museum on the Mall in Washington was not constructed yet. That was his portfolio, was to make the research flight gallery come alive. And in the process of that, he got to interact with all of the principals who were alive who did this work. He talked to the engineers, he talked to the pilots, and he literally wrote the book on the Bell X-1 and the D-558 programs. So that's Supersonic Flight and On the Frontier. Curtis Peebles worked at the NASA Neil Armstrong Flight Research Center and wrote the book Probing the Sky, which is the story of the early Round 1 research airplanes. And that contributed heavily to what I'll be sharing with you. Tony Landis, a photographer extraordinaire, now works for the Air Force History Office in Dayton, Ohio. He did the color illustrations and a lot of the photographic research for what you're going to see, as well as Chad Slattery, contributed photography. And then Scott Finn, the proprietor of Fiddler's Green, the world's largest collection of card models, extended to us these PDF models of the D-558, the -1, the Skystreak, the little red one here, as well as the Skyrocket, the D-558-2. So you have the Skyrocket there. It's a two-parter. You cut them out and glue them together with Elmer's glue. It works best if you put the Elmer's glue on with a little paintbrush. We won't discuss how I know that. Talk about the X-planes, and we talk about the X-planes today. The X-planes started with the Bell X-1. It was the first airplane built as a research tool to provide flight data when wind tunnels couldn't provide any data. And that series continues on today. Boeing in the Antelope Valley is currently working on the X-66. So it was a successful series, continues on today. So what is an X-plane? It's an experimental United States aircraft, and there are rocket X-plane designated also. It's used to test and evaluate new technologies and aerodynamic concepts. The X designators exist within the U.S. military system of aircraft designations, which denotes an experimental research mission. And that means that when Burt Rutan builds the Spaceship One and flies to space, and you have the first civilian astronaut, Mike Melville, that doesn't get an X designator. There aren't public funds supporting that. So what's not an X-plane by that definition? From 1925 to 1962, the Air Force, Air Corps, designated their experimental pre-production development aircraft with an X. So here you have an XP-51, and that was pre-production development airplane. If they thought that they were going to do service tests on those designs, they would give them a Y designation. So you'd have the YP-38. And that system continued on until 1962, when both the Air Force and the Navy and the Coast Guard and the Army and everybody else in the military forces who flew an airplane designated their airplane. They made a common designation system from 1962 on. So everybody did the same thing and called everything by the same name. And that was because, anecdotally, McNamara, who was the Secretary of Defense, was embarrassed one day looking at a spreadsheet because the spreadsheet had a Navy F-4D on one side with one price, and there on the other side of the spreadsheet was an F-4D that the Air Force had. And the price tags were radically different. And he wanted to know why the Navy was getting their F-4D so much cheaper than the Air Force. And what he didn't understand was a Navy F-4D was a Douglas Skyray. And an Air Force F-4D was an F-4 Phantom built by McDonnell Douglas. Camouflage version of the one that's behind you here. So from that point on, everybody had to call everything by the same system, and the Navy system was abolished. And unfortunately, the Navy system, coming from a Navy guy, the Navy system told you a whole lot more about the airplane than the Air Force system would. An F-4D would tell you if it was a Douglas airplane. The D told you Douglas built it. The F told you it was a fighter, and the 4 in the middle told you that that was the 4th fighter that Douglas had done, and they'd been at this for a while. But that system went away in 1962. And so post-1962, all X's just stand for experimental, and we still have in the system the service test pre-production airplanes with the Y. And you might remember that for the lightweight fighter competition, you had the YF-16 and the YF-17. Following that, for the Air Force's stealth fighter, there was a fly-off. There was a stealth fighter fly-off, and that was between the YF-22 and the YF-23. And then the marketing departments got involved, and so for the Joint Strike Fighter, you do not have the YF-32 and the YF-35. You have the X-32 and the X-35, and it's called the Battle of the X-Planes, and it makes a great PBS special. Anyhow, like I said, marketing, it makes the world go round. So a backstory on compressibility effects. This is a review from the X1 presentation, but 1687, Isaac Newton calculates the speed of sound, and he gets it within about 15%. And then there's a progressive incremental understanding of what's actually happening. 1742, there's data on artillery projectile drag rise, and they find out that it's not a linear squared function, it's a cubed function. Something different is going on when you get faster than the speed of sound. 1820, sound wave propagation is correctly calculated by a Frenchman named Laplace, so we have the speed of sound in 1820. In 1887, Ernst Mach, who gives us his name as denoting what the speed of sound is. We talk about Mach 1, Mach 2, Mach 3. That all goes back to Ernst Mach. In 1887, he takes the first photograph of a shock wave. In 1918, doing propeller research for the U.S. Army Air Service, they realize that there is a critical Mach number, and above that, the propellers don't function well. So critical Mach number shows up in 1918. Between 1924 and 1929, they start to do research on compressibility effects and flow separation. Again, this is on propellers. Airplanes are flying 150 miles an hour, but the propeller is turning fast enough to have a transonic flow, have a shock wave, and lose efficiency. In 1933, John Stack, an NACA researcher, proposes a high-speed research airplane for the first time. Up to that point, you had military fighters that were fast airplanes, and there were racers that were fast airplanes, like the GB that you have here. But no one was building fast airplanes and instrumenting them to collect aerodynamic data. So that was a new idea. Need to have a research airplane. The first Schlieren shockwave image of an airfoil is taken by Eastman Jacobs and John Stack, same researcher. 1940, they realized that the wind tunnels stopped giving accurate data above 80% of the speed of sound. Between 0.8 Mach and 1.2 Mach, the wind tunnel data was corrupted, and it was not usable, and they weren't able to evaluate what was going to happen on a shape. So that was wind tunnel choking, and it was an academic thing, and it was academic up to, for the US, up till 1941, when compressibility effects with the YP-38 produced tuck under. The airplane broke up in flight, and test pilot Ralph Verdon was killed. So it goes from something theoretical to something that bites. Going back to John Stack, in 1931, he starts sketching out a proposal for a research airplane, and he wants to do this because he understands that because of transonic flow and compressibility, the faster you flew, the worse it got. If you had a region of the airframe that had transonic flow, you would have decreasing lift, and that was bad. You would have increasing drag, and that was bad. And then you had an increase in the pitching moment. The nose would drop, and that wasn't good either. And since the wind tunnel wasn't able to deliver on those kinds of questions, there was a proposal that he published in 1933 for let's have a research airplane. He was inspired by the Schneider Trophy races, which had just flown seaplanes at about 250 miles an hour in Hampton Roads, in the Chesapeake Bay. And when he saw that race and saw what the Rolls-Royce engines were doing at that time, he concluded that if you had a 4,000 horsepower propeller driven airplane powered by a Rolls-Royce engine that you could get into the speed regime where compressibility became a factor. And that was around 566 miles an hour that he had theoretically. So that was in theory. In-flight compressibility effects start showing up in the Curtiss P-36 of 1937. There was a 600 mile an hour vertical dive by company test pilot Lloyd Childs, and he was losing elevator effectiveness. Brewster, the F-2A Buffalo, was tested and evaluated by the NACA in Langley. And part of that was to do dive tests at that. And again, they were getting up in the 550 mile an hour range in vertical dives. And again, experiencing compressibility effects. The controls got very heavy, and elevator effectiveness was in question. And in addition to those, the Messerschmitt, the early Messerschmitt, the B model Messerschmitt, had a fatal crash in 1937, which was attributed to compressibility. Pilot dove into the ground, and again, Lockheed and the YP-38 had a bad experience in 1941. Airplane broke up in flight. As a result of that in-flight experience, the NACA at Langley Memorial Aeronautical Lab in Hampton, Virginia, did some prototype work of an all-movable tail on the Curtiss XP-42, and that's what you see here. The XP-42 was a proposed upgrade for a Curtiss P-40. It never went into production, but the NACA had the airplane there and used it as a test bed. And while all that's going on, we have the unexpected arrival of the jet age. Von Ohain develops an axial flow jet engine, and it is flown in Germany in 1939. And Frank Whittle develops a centrifugal flow jet engine, and that is flown in 1941. The United States flies a jet airplane in 1942, and the Luftwaffe starts flying the Messerschmitt 262 in combat in 1944. The jet age meant that not only could an airplane fly fast, but it could continue to use all the thrust that was available without the degrading effect of having a propeller on the front end of the flying machine. And so what that means is that not only are airplanes able to fly fast doing operational military flying, diving from high altitude, but you were going to be able to have transonic flight in level flight with a jet engine. And the wind tunnels could not provide information for that region. So the origins of the American X-plane series as we know them today, I've already mentioned John Stack's transonic research airplane to study and resolve the issues of compressibility. But December 18th, 1943, which is the day after the December 17th Wright brother lectures, one occurred in the UK with a US lecturer, and there was a parallel lecture given here in the States by W.S. Farron of the Royal Aeronautical Establishment. And after those Wright brother lectures, Farron has a meeting at the NACA with the senior U.S. aeronautical R&D leaders, and Bell's Robert Wolfe proposes a transonic research airplane. And what the Americans didn't know at that point was that the British had already started working on the Miles M52. They had issued a contract to Miles to build a jet-powered 1,000 mile per hour flying machine. And so that work had already started, at least in concept, in February of 1943. So everybody around the table, it turns out, was in violent agreement that you need to build a research airplane to attack these problems. March 16th, 1944, there's another meeting at Langley, and that marks the origins of a twofold approach by the Navy and the Army Air Force, each relying on the NACA for technical support. And the reason that there's a twofold approach is that the Navy sees that the aerodynamics of the airplane are changing. The low speed characteristics of airplanes are changing, and they are committed to naval aviation, which takes airplanes to sea on ships. And so their need was to have the technology for the next generation of Navy fighters. The Air Force, on the other hand, had been doing some high-speed work already, understood the value of the rocket engine, understood that a rocket engine could propel you supersonically, and the Air Force desire was to fly supersonically as fast as possible. And so this is the Air Force approach. A rocket-propelled airplane looks a lot like the John Stack configuration that we saw a little bit ago. And again, rocket-powered. Ezra Kocher had been working with the XP-79 concept by Northrop, which was a rocket-powered tailless fighter, and that ultimately only flew under jet power. But Ezra Kocher had gotten a sense of what could a rocket engine do for you. And since there were people who hypothetically would advance the idea that the drag rise as you got closer to Mach 1 turned asymptotic, and maybe it would not be possible to fly faster than the speed of sound. So he named his proposal the Mach .9999 proposal, tongue-in-cheek, just going, I don't want to have that argument around this table, I want to get money and build this airplane. So, Douglas D-558 Skystreak is representative of what the Navy wanted, and it coincidentally matched with what the NACA wanted. The NACA was not especially interested in flying supersonically. Their wind tunnels were providing data at 1.2 Mach and higher, and they understood that there were no showstoppers above Mach 1.2. What concerned them was what is happening in this region between 0.8 Mach and going supersonic, so their interest was in a transonic airplane. And they also knew that the transonic flight was very dangerous, and they were interested in minimizing the risk and having a long, methodical research program where you flew a number of airplanes on many flights and incrementally built up your knowledge base so that you could do this more safely. So to that end, the Navy and the NACA both wanted a conservative ground launch airplane, and they were not interested in anything faster than the speed of sound. They weren't even interested in breaking Mach. So the Douglas D-58 program comes out of that, and there's three phases to it. The D-558-1, the little red model here, has a straight wing. It has a jet engine, and they propose 6 airframes. With what they learned from that, they hope to build a phase 2 with a swept wing and have combined jet and rocket power to fly faster. They had a phase 3, which was a hypothetical production combat aircraft after that. And as time progressed, because this program goes on for almost a decade, there was a revised phase 3, which looked a lot like the North American X-15. And because it looked like what was going to become the North American X-15, it was canceled to avoid a duplication there of effort. Here's an early mock-up of an early configuration for the D-558-1 Skystreak, and you'll notice that it has a nice pointed nose on it. There was a thought within the Navy proposal that Douglas could morph this into a first-generation combat jet aircraft for the Navy to use. And so they put the air intakes for the jet engine on the sides of the fuselage, and in that concept, in that configuration, you have room to put armament in the nose. That was one way of attacking it. They had a number of other configurations. Here's another one that has a different wing, a different tail, forward swept wing on this. The forward swept wing did not fly until the 1980s on the Grumman X-29, but forward swept wing research airplanes were always on somebody's short list. So this is a cutaway of the D-558-1 Skystreak, called the flying test tube. And when you see the profile on the fuselage, that'll become a little more apparent. One of the design requirements was to have no protuberances from the fuselage, which would make their own individual shock waves and complicate the process of collecting the data. But it has a straight wing, it has a 10% thick airfoil, and the wing on this is actually a lower aspect ratio wing than what Bell put onto the Bell X-1. So this is February 4th, 1947, a Douglas factory display. And what you see here in this is ship number 2 disassembled so that people can see inside. There's very little structure inside the fuselage. It has a 1/10 inch thick magnesium skin, so to carry monocoque loads over that and optimize the internal volume on the airplane. And the Skystreak was built with the same 500 pounds of flight test instrumentation that the Bell X-1s carried. Here is the Skystreak early in its career. This is ship 1. When you see the name of the airplane painted out on the nose of the airplane, this time it says Skystreak. When you see Skyrocket on the D-558-2, that's an indication that is the contractor's phase of that program. Douglas pilots are flying it at this point. And so here it is at North Base. You'll note the early fuselage insignia does not have the red bar in it, and that's handy for dating some photos. The red bar is added to the national insignia in January of 1947. So here is the D-558 Skystreak right before its first flight. It has a low-speed canopy on it. You'll see that the canopy hinges on the front. The D-558, both the Dash 1 and the Dash 2 and the Bell X-1, none of those airplanes had ejection seats. So in the case of the Douglas airplanes, they were designed for emergency egress for the nose to jettison. The nose could be jettisoned from the airplane with the pilot's seat. The pilot would, once he was clear of the rest of the airframe, would just jump out the back. And the thought with that was that you're not going to have any problems down low. There's nothing tricky about flying down low. If there's an issue with egress, it's going to be at high speed, at high altitude. And so the canopy is hinged on the front. And that means that if you have any airspeed at all, the pilot is not going to be able to open that canopy and jump out. Here you have the first flight, Skystreak, Douglas test pilot Gene May. It's April of 1947. By this time, the Bell X-1 has been flying for over a year. Glide flights on the part of the contractor and some early power flights. This is Chad Slattery's photo of the Skystreak that's at the Naval Aviation Museum in Pensacola. You see how straight the fuselage is. That's how it got the nickname test tube, and because they painted them red for high visibility, they were called the Crimson test tube. The canopy has changed to a high-speed configuration, but it's still hinged on the front. But the Skystreak was a very small, very compact, and very fast airplane for its day. And it was, after the initial flights were made by the contractor, the Navy and Marine Corps started a workup campaign to go for the world speed record. The world speed record changed hands very quickly in those days. It was set in September 1976 by this Gloucester Meteor 4, 615 miles an hour. That was September 1946 in the UK. If you remember hearing about Jeffrey de Havilland's crash of the de Havilland 108 Swallow at high speed, that was later that same September. Again, trying to raise the mark of the world speed record. The de Havilland Swallow was a tailless prototype for a tailless airliner. And based on the data that they were getting from the de Havilland Swallow, they decided that they wanted to put a conventional tail on the de Havilland Comet airliner. But it was not built. It was not built in the same way as the X-1 or the D-558 program. It was for configuration information on how do we build an airliner. It was not designed to be a supersonic airplane. But world speed record, 1946, 615 miles an hour. It falls to the Lockheed XP-80R at Edwards Air Force Base in June 1947. 623 miles an hour, piloted by Air Force Colonel Al Boyd. Al Boyd is Chuck Yeager's boss, if you remember that part of the story. And to get this XP-80R fast enough to set a world speed record, they modified the airplane, and it had a smaller canopy. They reduced the span on the wing, and they also put water injection on the engine. And that's how they got the XP-80R to hold that record. And that stood until August of 1947. August 20th and August 25th, there are two records set using the first two Skystreak airframes. The first record was set by Navy Commander Turner Caldwell flying the #1 Skystreak, and he set a world speed record of 640 miles an hour. And in doing that, when they tuned the engine on the ground, they tuned it to 100% maximum RPM on the ground. But when he got in the air, he realized he was only indicating 98%. And so using that information, Marine Colonel Marion Carl had his Skystreak tweaked on the ground to more than 100% RPM, so that when he was up making his speed runs, the engine was at the test point of 100% thrust. And so he raised the speed mark to 650 miles an hour. This is August of 1947. That is the world speed record. When the Bell X-1 flies supersonic in October of 1947, that's not a world speed record in any official way, because to set a speed record, you had to take off under your own power from the ground, fly your flight, land, and the pilot had to live for 2 weeks. So those were the rules, and so these were official speed records that stood even though the X-1 had flown supersonically. How many of you have heard of Marion Carl, the Marine Corps pilot, who set that record? A couple of you? Okay. A lot of times people will say, "Oh, well, Marion Carl, well, he was the Marine Corps' Chuck Yeager." If it's a cocktail conversation, that's okay. But who was Marion Carl really? Well, Marion Carl flew at the Battle of Midway and scored. He flew the campaign defending Guadalcanal. He fought the best pilots the Empire of Japan could field, and had 18.5 kills flying the Grumman Wildcat against the Zero, which is kind of like taking a bulldozer to a knife fight. And so that was kind of Marion Carl's career. And then went on to become a test pilot in 1945. Now, Chuck Yeager, on the other hand, great American hero, has 11.5 kills. He is flying the P-51 Mustang later in the war. Marion Carl is fighting the Japanese when the Japanese are still on the offensive and winning. Chuck Yeager is flying against what is left of the Luftwaffe, flying the P-51 Mustang, which is on everybody's short list of the world's greatest World War II fighter. So whenever Marion Carl comes up, the intellectually honest way to understand who Marion Carl was Chuck Yeager was the Air Force's Marion Carl. And that's all I have to say about that. Okay, so the Douglas pilots have proven that the Skystreaks meet all of the specs that they're supposed to make. The Navy has gone in along with the Marine Corps and set their speed records, and then it becomes the NACA's turn to start flying these airplanes for what they were designed for, and start collecting a large body of flight data. And disaster comes in May of 1948 when NACA pilot Howard Tick Lilly has a compressor failure on takeoff and crashes onto the lake bed at Edwards. And the NACA had been flying research missions since 1915, and this crash in 1948 is their first fatality. And it causes them to go back and take a look at how the airplane was configured. And as a result of that, they put a redundant control system in the airplane. They armored the fuel lines and made the airplanes a lot more robust, and flew out the research program without any other incidents. So the D-558 Phase 1, it's an intentionally conservative subsonic airplane, but it provided the first comprehensive transonic database for all of industry to use going forward. There were airplanes that were just as fast as that. You saw the P-80R, the early fighter. There were fast airplanes, but there were not fast instrumented airplanes that were being flown in a disciplined way. And so the D-558 provided the first comprehensive transonic database across a broad range of speeds. And where the X-1, when it was air launched, had 2.5 minutes of power and could give you seconds of data on condition, the Douglas D-558, the Skystreak, could fly for almost an hour and could bring back a lot of test points. So, getting into Phase 2. Phase 2, again, it's the Skystreak. It's proving, or the Skyrocket, and it is proving the swept wing. Again, this is a ground launch design. It's supposed to take off with a jet engine, land with a jet engine, use its rocket engine in between. So it's a complex airplane with a composite power setup, and it is still not a supersonic design. It's designed for 0.9 Mach. Here's a cutaway for the Skystreak, and what you see on this is a 35-degree sweep angle on the wing, a 40-degree sweep angle on the tail, and if you look here at the nose, it has the same contoured cockpit canopy that the X-1s were designed with. And based on the X-1 experience, where the pilots really couldn't see the runway within 2 miles without banking the airplane, they changed that configuration. The only swept wing data that the U.S. has when this haul starts is what has been captured from the Germans with the Operation Paperclip activities post-war. And so the United States Navy has a contract with Bell Aircraft to build a swept wing and put it on a P-63. A P-63 King Cobra, not a Bell Aerocobra. They put it on a P-63 King Cobra, and then they keep the rest of us confused forever by calling it an X-39 or an L-39. But this was a low-speed wing configuration. Again, the Navy's interest is getting fast airplanes to slow down and land on carriers. So this work was done through Navy funding, and that airplane went to the NACA, and that was their only real experience with a swept wing airplane. Here you see an F-86 and a Douglas skyrocket, they both have that 35-degree swept wing. Turns out they're both designed at the same time and they're both constructed at the same time. They're contemporary airplanes, and again, just based on based on captured data, moving forward with that. The sweep on the tail was a 40-degree sweep, and that was to raise the critical Mach of the tail, so that if your wing was compromised by shock waves, your elevator was still going to work. So here's the rollout configuration. Again, there's that conformal canopy on the prototype. You ask about the air intake. There's the air intake for the jet engine that's on the skyrocket. So here's the first flight configuration, February 4th, 1948, and what you see here is the cockpit has been modified. You can now open that. Open that cockpit with airflow on the airplane. It still has a short tail. When they increased the side area of the airplane by putting a raised canopy on it, they made it directionally less stable. So that tail was raised 14 inches. And here's the exhaust. Here's the exhaust for the turbojet engine. The thought was you're going to take off under jet power, get up to where you get up to your test altitude, and then use your rocket engine to get your high-speed test points. So that was the thought for taking off on the lake bed with this. It was designed for ground launch. That was a 3,000 pound thrust jet engine on it, and the first takeoff roll was 15,000 feet because the rocket engine wasn't ready yet. They decided they were just going to do the early flights with that. The engine was ready, but the turbo pump was not. It was the same story as the Bell X-1. So while they're waiting for a turbo pump, they fly this just under jet power to get their low-speed test points. But they decided that JATO bottles were really a great idea for shortening your takeoff run, and so this is with the jet engine plus the rocket pack JATO bottles for takeoff, and that made things dramatically better. You only needed 8,000 feet of runway, and when they finally got the rocket engine installed in the airplane, said let's see how short a takeoff roll we can actually get, with the jet producing 3,000 pounds of thrust and the rocket engine producing 6,000 pounds of thrust. The takeoff roll was reduced to 2,600 feet. Dramatic improvement on that. The problem was you used up all your rocket fuel before you got up to altitude. So it was a nice idea, but their optimum configuration turned out to be 4 JATO bottles and the jet engine. I mentioned earlier it had the same engine as the Bell X-1, and that was actually a Navy engine. It was the XLR-8. It was developed by the U.S. Navy that had a need to get flying boats off the water sooner. So JATO bottles and the XLR-8/XLR-11 engine were both Navy initiatives. The only way to tell the difference whether it's the Navy version, the XLR-8, or the Air Force version is the 11, is you look at the nozzle pattern. And on the Navy version, the nozzles are arranged in a square, and if you look at the back of an X-1, it's a diamond-shaped pattern. The two center chambers are just squeezed in a little bit, and aside from that, they're the same engine. So in the full-up configuration, the Skyrocket carries 260 gallons of aviation gasoline for the Westinghouse 3,000-pound J-34 thrust turbojet engine, 195 gallons of ethyl alcohol and water mix for the rocket engine, and they use 180 gallons of liquid oxygen for that. So it's a So compared to the Bell X-1, which carried 100% of its load in rocket fuel, the pilot for the Skyrocket was trying to hit his test points while conserving the fuel that he had. Here's the Skyrocket. This is ship 3, which has the jet engine and the rocket engine in the back, and the XLR-8 is helping on the takeoff. Midway into the program, there was a decision made to make the D-558 Skyrocket completely rocket-powered and air-launch it. By this time, there's a body of knowledge with the Bell X-1 that shows that air launch was a lot safer than they had originally imagined, and it optimized all of the fuel that you could carry on your test machine. So ship 2 and ship 3 were modified for air launch. Ship 2, the jet engine was removed totally, and so it had the largest capacity there. But the advantages of air launch, with just a turbojet engine, the Skyrocket could max out at 585 miles an hour. If you used the mixed power of both the XLR-8 rocket engine and the jet engine, that went to 720 miles an hour, which is still only Mach 0.9. And when the Skyrocket was modified to use all of its internal capacity for oxidizer and rocket fuel, that gets an airplane that can go 1,250 miles an hour. The propellants in ship 2 were 345 gallons of liquid oxygen and 378 of the alcohol water mix. So it made a big difference to modify the airplanes. This is the Navy version of the B-29. The Air Force transferred a B-29 to the Navy. It was called a P2B-1S. And unlike the X-1, where they dug a loading pit into the ground and put the X-1 in the loading pit to connect it to the bomber, for the Skyrocket program, they put hydraulic jacks out on the ramp, and they would lift the bomber in the air, which looked like a really elegant solution, except that the wind blows in the desert in the afternoon, and having the bomber perched up on the jacks just made things trickier than they needed to be. So they found that it worked out just fine to put the bomber on jacks that you would use for swinging the landing gear. Worked just fine to put the bomber in the hangar, jack it up, and do all your work out of the wind. And you can see all the successful air launch silhouettes there on the side of the bomber. By 1955, a young guy named Neil Armstrong had just wrapped up his Korean War combat tour, gone back to Purdue University, finished his aeronautical engineering degree, came looking for a job, and ended up flying in the high desert. And one of his jobs in the high desert was to fly along with Stan Bouchard for the launch of the Skyrockets. And here they are pulling the props through. Again, this is 1955. If you look at the belly of the Skyrocket, you can see that it's only about 18 inches off the ramp there. Some legendary Skyrocket pilots here. You see Bill Bridgman, Marion Carl, who comes back, and then NACA pilot Scott Crossfield. And of the three of them, Bill Bridgman manages to fly the Skyrocket at Mach 1.88, sneaking up on Mach 2, and he gets to an altitude of 79,000 feet. Marion Carl flies the airplane to 83,000 feet in a pressure suit and gets to Mach 1.78. And at this point, it becomes obvious that the Skyrocket is almost within range of being the first Mach 2 airplane, but not quite. And at 70,000 feet, the sky is turning dark. You can see the curvature of the Earth. there's a lot of excitement with that. And the NACA discovered that if you put nozzle extensions on the rocket engine, that you could get another 6% of thrust out of the engine. And they make the argument that it's really worth flying Mach 2 in the skyrocket to get Mach 2 data. And so on November 20th, 1953, with a waxed, polished, sealed sealed skyrocket, Scott Crossfield takes off and flies a Mach 2 profile perfectly. Reaches Mach 2.005, 1,291 miles an hour, and everybody is set to celebrate the 50th anniversary of the Wright brothers' first flight the next month with this milestone.
What did they do to the rocket to get the 6% increase?
They put an extension on the nozzles. Have you seen the movie Rocket Boys?
Yes.
Okay. Every rocket nozzle is a compromise. The atmospheric pressure is 1 atmosphere on the ground. The higher you go, the less the pressure is, and so your optimum shape for a bell nozzle on a rocket engine is altitude dependent. And so Saturn V's and everybody else, you just picked your best guess and you went with that. And so for this, they said, we can put a nozzle on that's optimized for that high altitude profile and squeeze out another 6%. So, sometimes it really is rocket science. So anyhow, so these 3 gentlemen are the high watermark of the people who flew the skyrocket and put it into history. Here's a ground test engine run in the all-rocket configuration, no jet engine. This is ship 2. This is the one that hangs in the Smithsonian, and I don't know if you, I don't know how well you can see this photo, but right underneath the stabilizer is a little protective shield so that they can run the engine on the ground and not bang up the tail. You'll also see that this is before the creation of OSHA, because the technician on the ground is in shirt sleeves and no hearing protection, and that's a loud engine. Okay, so here's Bill Phillips' Mach 2 painting, Mach 2 Dawn, just to commemorate the milestone. Here's Crossfield handing off his kneeboard. Here's the press conference when he lands from the flight. Again, they understood no bucks, no Buck Rogers way back then. The public hadn't heard about any great Mach-busting milestone since 1947. This is now 1953. So there was a press conference after he landed, and then here's all the technicians. After the press goes away, they can get in and download all the instrumentation and get the data from the flight. And here laid out on the wing, 634 pounds of instrumentation again, this is to build up the database of how do you build the next airplanes. So it's a 12-channel oscillograph, a 60-capsule manometer, transmitters for data on the control wheel and rudder pedal forces, recorders for positions of the ailerons, elevators, rudder controls, an accelerometer, and telemetry that would transmit airspeed, altitude, acceleration, and the position of the controls. An airspeed and altitude recorder, a side slip transmitter, and over the pilot's shoulder is a camera, a movie camera that is, it's a fighter plane gun camera, just taking a picture of all of the instrument readings over the pilot's shoulder. So that's what's going on the airplane. And then when you land, that's a photographic light table, and everybody pulls all the strips out of the oscillograph and gets dividers out, and you measure all the wiggly lines to get your data. After the Mach 2 milestone, there was still work for skyrockets to do. When you put G on the airplane, if the pilots pulled the stick back and started putting 4 to 6 Gs on the airplane, the skyrocket had a profound nose pitch up, and then it would go out of control. The nose would pitch up, and then the pilot became a passenger until the airplane recovered itself. And so they started a very detailed campaign for what can you do to the wing of the airplane to mitigate pitch up. And what was happening with pitch up is, with a swept wing, the wingtip would stall first. Well, the wingtip on a swept wing airplane, the wingtip is way back behind everything else. It's behind the CG. And so when that part of the wing starts lifting, the nose comes up. And so that was, and the nose came up because of that loss of lift at the tip, and also because the wing wake would blank out the elevator. So these are a number of the different configurations. They tried wing slats, they tried wing fences, they tried all kinds of stuff, and at the end of the day, they said, it'll work out a lot better if you put the stabilizer on the bottom of the fuselage instead of halfway up the tail. The other thing that the skyrockets did was look for what are the optimum shapes for external stores. If you want to put fuel tanks on an airplane, what shape should they be? What loads do they put on the airplane? And so that was where we got our high-speed drop tanks. And also, if anybody has dropped ordnance off of a U.S. airplane from about 1960 on, that was the Mark 82 series of weapons. We're still using those shapes today. So the Round 1 transonic research airplanes were all about sorting out what works. And these are the airplanes that were in the stable in 1953. And going around, you have the X1 here. You have the X3 in the middle, X4. The X5 is in the back corner. And you have the Delta Wing XF92A in the mix back there. Anybody here ever meet Bill Channa? Mr. Delta Wing? Okay, well, that's, so there you have it. That's the Delta Wing XF92A. And Scott Crossfield flew that airplane extensively. Scott Crossfield was also part of the team that flew the replica Wright Flyer. And from his description, the only airplane that flew worse than the XF92A was Wilbur Orville's Wright Flyer. So so these are the airplanes that together build the database for going forward, and this is round 1 of all the transonic research aircraft. So what you have is X1, X3, X4, X5, and and a couple of airplanes there that always get left out of the sequence because they don't have X-plane designations. And this is the Mach 2 stable. And just to recap, here is ship 1 of the Douglas Skystreaks. They started off painting them red, thinking that that would make them visible. And about the same time, they learned that an orange X1 was kind of tricky to see. They had the same problem with the red paint on the Skystreaks. You'd lose optical tracking on them between 10 and 15 miles if they were painted red. And when they started painting them white, you could track them out to 30 miles. So it was worth doing. You'll see that the surfaces are still red, and that's because they were balanced surfaces, and a coat of white paint would throw them out of balance and make them prone to flutter. And so they stayed red surfaces until they had a chance to redo them. Ship 1, the one that Navy Commander Turner Caldwell set a speed record in, is now in the Museum of Naval Aviation in Pensacola, Florida, and it's restored to its Douglas rollout markings. Ship 2, this is the one that crashed, killing Tick Lily. And this is Ship 3. One of the configurations it flew with was having tip tanks on the wingtips. And it is now at the Sullenberger Aviation Museum in Charlotte, North Carolina. So that's where those all ended up. Our Skystreaks. This is the Ship 1 Skystreak. And it is now in the Planes of Fame Museum in Chino, California. It was modified to an all-rocket configuration, but not flown that way. So it did all of its Douglas flying with the jet engine installed in it. Here is Ship 2, and it hangs in the Milestones of Flight Gallery annex. It's over the elevator at the Smithsonian Institution National Air and Space Museum. And Ship 3, again, there's the drop tank on it, and it is at Antelope Valley College in Lancaster, California. The program was wrapped up in 1956 because this is the standing army that it took to get a Mach 2 flight from an air-launched rocket plane. You needed a mothership and the test vehicle, and you had a low-speed chase and a high-speed chase, and it just took a lot of people. By then you had Mach 2 airplanes, like the F-104 Starfighter. And so if you needed Mach 2 data, there were faster, easier, less complicated ways to get it. And the airplanes were retired and are now on display different places around the country where we can see them. For the 50th anniversary of the first flight, NASA had a symposium called Toward Mach 2. The moderator for that symposium is Ed Schneider, and at the time Ed Schneider was a NASA SR-71 pilot, and after he retired from NASA, came here and wore red blazers with the rest of you. So some of you may remember Ed. But we had Stan Bouchard, Bob Champagne, Scott Crossfield, John Griffith, and Dick Hallian come out and share on a two-day event for that. That's one of the free books that you can download as a PDF. Dudley has the links for those. This is the other free book. This is the story of the Round 1 X-planes probing the sky. And it has a lot more detail. What you heard from me today is just, at best, it's just the Cliff Notes version of these campaigns. And so this is another book that's a free download from NASA as a PDF. Crossfield Drive, January 17th, 2012. Edwards Air Force Base honored Scott Crossfield by naming one of the streets after him. And if you know the joke, Chuck Yeager had the joke he never wanted to have a street at Edwards Air Force Base named for him. And that's because the streets at Edwards Air Force Base were named for the pilots who lost their lives doing test flying there. And so during Chuck Yeager's lifetime, they decided that although he said he never wanted to have a street at Edwards named for him, they named a street for Chuck Yeager. And they also named this street for Scott Crossfield. And it's a well-traveled street because on Edwards Air Force Base, it's between the Oak Club and the golf course. Here's Scott Crossfield for our Men of Mach 2 symposium I mentioned earlier. Antelope Valley College, it was raining. We wanted to get a picture of Scott with the skyrocket, but it was raining. And Chad Slattery, the genius aviation photographer that he was, had him stand under the roof of the porch. And so he's standing undercover, and the skyrocket's out there in the rain. And so that's the photograph that we have to memorialize that event. There was a question on, did the Skystreak ever fly supersonically? And there is a Douglas press release that says that it was supersonic one time in a long dive. And NASA picked up that press release and said, well, the company said that they flew Mach 1 with it. So there's a NASA fact sheet that will tell you that the that the Skystreak was supersonic once in a dive. And so from junior high on, I believed everything that I read. It flew supersonic once in a dive. And at that symposium in 1998, somebody asked the panel of pilots who actually flew it. So it flew supersonic once. And they all kept a straight face, and then one of them said, "Have you ever seen any data traces from that flight?" And so the press release says they did. The panel that we had was not convinced. Thank you. So to rephrase the question, it was about the all-flying tail, the moving stabilizer on these research airplanes. And the short answer is yes. It was a design requirement for both the Bell airplanes and the Douglas airplanes to have an all-moving stabilizer, to have a high rate moving stabilizer, leading edge on both airplanes, because they understood that once a shock wave set up on your elevator hinge line, you weren't going to have any elevator control. And so with their flight test data that the NACA had from the Curtiss XP-42, they knew that it was a legitimate control effector. That if there was a problem, that was going to allow you to solve the problem. And so both of those families of airplanes had a stabilizer that the whole stabilizer could move. It was called the all-flying tail. And that was backfitted to the the F-86. The early F-86s had a conventional stabilizer elevator arrangement, but the F-86E onward had an all-flying tail. And that gave the F-86 the ability, gave F-86 pilots the ability to have elevator control throughout their entire speed range. They could dive supersonic, and a MiG could not. The MiG-15s that they were facing off with in the Korean War did not have that capability. So the F-86s could fly faster and continue to maneuver with that. That's an excellent question, and for everybody who didn't quite hear that, it was what was the relationship between the Bell program, which was being funded by the Air Force, and the Douglas program, which was being funded by the Navy. And they started off as two independent programs. However, with the progression of time, they realized that the Skystreak, with its long flight times, could generate a lot of transonic data that was really useful. And it complemented the supersonic data that they could get off of the Bell X-1s. And there was a huge spreadsheet database that needed to be filled out for the high transonic but not supersonic test points. And that work ended up being done in a very complementary way by the Skystreak. That freed the X-1 to use all of its flight time on high-speed test points that it couldn't reach. So the Skystreak was very complementary with respect to the Bell X-1. Remember, Bell had a follow-on Air Force program to the X-1 with a swept wing, and that was the X-2. Both the X-2s were destroyed very early in their test programs. One was an in-flight explosion while it was still mated to the bomber, and that was traced to hydrocarbons in the gasket in the liquid oxygen tank. Liquid oxygen doesn't like hydrocarbons, And that's where the explosion for that came from. But they lost one airplane that way. They had one Mach 3 flight, Mach 3.2, with Mel apt, and they had inertia coupling when he tried to return to the base, and so that airplane crashed. So the airplane that they had hoped to get a lot of swept wing data from, the X2, those were gone. And without the without the X2, they had the swept wing. They had the swept wing skyrocket there, fully instrumented, and that's where they got their swept wing test points. So the long answer to your question, they were designed to be independent programs. They ended up supporting each other very well. They supported each other so well that as people looked back at it in hindsight, everybody thought, oh, well, they intended to do it that way from the very beginning. And that wasn't the original intent, but it worked. Yes? So the question about magnesium, the Skystreak and the Skyrocket both had magnesium skins on the fuselage for weight savings. The wings were conventional aluminum structure. But yeah, there was magnesium there, but that was, but again, that was just for weight savings. They had no problem with them, with operationally. It was tricky to. It was tricky for the museum in the Carolinas to restore the one that they got because the magnesium had corroded badly. So the restored Douglas Skyrocket in Charlotte, North Carolina, that one has been reskinned with aluminum on the fuselage. The question was the purpose of the divider in the center of the inlet on this, and you can't quite see it in this view. The cockpit was very cramped in these airplanes because the air inlet fed down both sides of the fuselage outside the cockpit. So the cockpit was squeezed in, and so that's just channeling air around the pilot into the jet engine. Question in the back.
No area ruling was applied to any of these aircraft, right? Even though the Germans and the inkling of the phenomenon and Richard Whitcomb had discovered it in 1972. So
Yeah, these are 1945 airplanes, and a Junkers engineer who went to work for Martin in Baltimore when they built the XB-51. It had two podded engines on the outside of the fuselage, which seemed like a funny place to put two engines. And in hindsight, they realized that was done for area ruling before people were talking about area ruling. There was a little bit of area ruling on the fuselage wing intersection on the Skyrocket. The airfoil at the wing root is a 10% airfoil. The airfoil at the tip is a 12% airfoil. So with this airfoil being smaller, you have a little bit of area ruling going on here. But again, to your point, Whitcomb was publishing on it. It was area rule that made the Convair F-102 a faster supersonic interceptor. Oh, yep. After the F-102, every manufacturer and their brother made an area-ruled airplane. Yeah, and so there was a lot of area rule, and you don't see it. You don't see it today. And I asked someone one time, how come we don't see area ruling today? And they said, we have a lot more engine thrust today than we had then. Area rule mattered if your thrust was limited and you were trying to punch through this transonic drag rise. Once you get shock waves over the whole airplane, aerodynamically everything gets really simple and life gets easy. But it's getting there in the first place that was the challenge.
thank you.
Very good.
Okay, thank you very much for your time and attention.